Dear learners, greetings from IIT Guwahati. We are in the course Applied Thermodynamics, and in the first module, that is review of thermodynamics or basic concepts, we are now in the lecture number 2, that is heat and mass transfer and laws of thermodynamics. So, in this lecture we will touch upon some of the important concepts such as heat and work transfer. So, here we will basically give the definitions of heat and work with a viewpoint of thermodynamics. Then we will discuss about zeroth law of thermodynamics. It will be followed by first law of thermodynamics. In fact, first law of thermodynamics has a very significant impact for most of the applications. So, in this regard we will discuss about some elementary thermodynamic processes that will be routinely used in our applications, which will be subsequently covered in the subsequent module. Then we will touch upon energy balance and steady flow energy equations, and the application of this steady flow energy equation we will try to see that what are the steady flow devices that can use these equations to solve some elementary problems. So, let me start the first topic, that is heat and work transfer. Now, here heat and work, these are the two terms of energy, although they are two terms of energy, but their philosophy of looking at the situation is different. So, basically these are the two mechanisms by which energy of a closed systems can be changed, and these two modes of heat transfer is known as energy interactions. Either it can be work mode or heat mode. And the first one, which is the heat transfer, it is the form of energy that is transferred between the systems and surroundings by virtue of temperature difference. So, the temperature difference means it is due to heat transfer. Now, any interactions which does not involve the temperature difference, we recognize it as a work transfer. So, the thermodynamic definition of energy interaction is by two modes, either heat or work. If it is a temperature difference, the mode of interaction is heat. If it is anything that is not due to temperature difference, that we call this as a work transfer. In fact, in a closed system, if you look at the terminology that we are going to use, either it can be heat addition or it can be heat rejections. When it is a heat addition, we say Q is positive. When it is a heat rejection, we say Q is negative. Side by side, if you look at the work transfer, when heat is added to systems and the system delivers some work, so in that situation we say it is a work done by the system, so it is a positive. And when heat is rejected from a system side by side due to the work interaction, then in that case we can say when Q is negative, work is positive, Q is positive, work is negative. So, those terminology we will be using in our applications. So, it is very important to recognize when it will be heat transfer. When the heat transfer is considered as a positive, at that time we have to take the work interaction as negative. If it is work, so done by the system, there are two terms used, work done by the system, by the systems, work done on the system. So, when it is work done by the system, so we recognize it as a positive. When it is work done on the system, we recognize it as a negative. Similarly, for heat may be added, so we say it is a positive. When heat rejected, it is recognized as negative. So, these terms we are going to use. Another important similarity between heat and work transfer is that both are recognized as a path functions. So, it depends on the path. So, if you look at the PV diagrams, a system undergoes a change of state from 1 to 2 in 3 different paths A, B, C, and of course, when you define them as a path function, the process needs to be a quasi static one. And since they are path functions, so they are not exact differential. Now, once you say recognize a energy interaction heat, then what else we can recognize as a work? So, there are thermodynamic way we recognize this work. So, we can have a mechanical form of work or non-mechanical form of work. The mechanical form of work means displacement work or moving boundary work, shaft work, spring works, work done by the elastic bar, work associated with stretching a liquid films, work required to raise and accelerate the body, rising the body or accelerating the body. So, these are the different forms of work. Now, accordingly one can find out the work transfer in this kind of applications. So, of course, when you recognize this work, these are the different applications what you see here. First one maybe we are mostly using by the shaft work, it is mostly used in thermodynamics or IC engines. Spring work, when the system is getting compressed or expanded through spring. There is a work done in the elastic bar. So, normally this work we are using in the topic solid mechanics. Work associated with stretching a liquid film, this is normally used when you deal with the bubbles formations, and that is due to the capillary actions, and we are using it in the fluid mechanics. Work done to raise the system or raise a body, so it is due to potential energy. Work required to accelerate a body, so we require a thrust. So, all these forms of energy we can compute the work transfer. However, apart from this mechanical work, we also have non-mechanical form work which we are not at all using in this course. So, they are like electric work or magnetic work. So, these are the some examples which has been given, like this particular situation is a piston motion within a cylinder. So, you can recognize this as a PdV work, and the rotation of a shaft we can say it is a shaft work. So, elongation of a spring we can call this as a spring work. Elongation of an elastic bar we can call it as a elastic work. The soap bubble expansion in a liquid film is known as a surface tension work. When we are going in an uphill, that means we are going in an inclined path, so we are rising a body, so we require a gravitational work. Then when we are moving on a horizontal surface in a vehicle, so we can say it is a work to be done for while due to the change in the kinetic energy. So, it is a acceleration work. So, all this kind of mechanical form work we are commonly used in our day to day life. Now, having recognized these things, now let us move to laws of thermodynamics. The first law is which is known as zeroth law of thermodynamics. So, this particular law has a significance, it gives the indication of a temperature. So, it talks about temperature is one of the property, and it says that if two bodies are in thermal equilibrium with the third body, then they are also in thermal equilibrium. That means, if temperature of body A is equal to temperature of body C and temperature of body B is equal to temperature of body C, then temperature of A and B are they are equal. Now, when we are talking this as a thermal equilibrium, then we have to say that both have same temperature readings when they are not in contact. So, the basic significance of zeroth law, it gives the indication of a temperature which is nothing but the measure of hotness and coldness. Now, to quantify these temperatures, we require some scale, temperature scale, and the temperature scales are quantitatively defined through ice point or steam point in two coordinates, one is in the degree centigrade, other is in the degree Fahrenheit. So, ice point in the centigrade scale is recognized as 0 degree centigrade or 32 degree Fahrenheit. Similarly, boiling point of water is recognized at 100 degree centigrade in centigrade scale and 212 degree Fahrenheit in the Fahrenheit scale. So, these are the estimates, but one important thing here that when you keep the measuring of the temperature, we require a working fluid, but the temperature scale and Fahrenheit scale does not be represented without any working fluid. So, to counteract this, we have another scale which is known as Kelvin scale. Of course, this Kelvin scale came up when we have second law of thermodynamics, that means this Kelvin scale came up after we recognize the second law of thermodynamics, and here the temperature scale is independent of properties of the substance. So, this is the one of the significant scale and we call this as a thermodynamic temperature scale, and in fact till date the lowest temperature that we have is 0 degree Kelvin. So, this is what we have 0th law of thermodynamics, it gives the sense of temperature. Now, moving on to first law of thermodynamics. So, we all know that from our basic instinct that energy can neither be created nor be destroyed, but it can change only its form. So, this particular principle is based on the experimental observation. So, we call this as a conservation of energy. So, based on this conservation of energy, we say that amount of energy gained by the system must be equal to the amount of energy lost to the surroundings during an interaction process between system and surroundings. So, since we are dealing with thermodynamics, this interaction is only by two modes, heat or work. So, this particular example I have given that when we have a heat interaction and when some situation we have work interaction for a closed systems. But with a viewpoint of work and heat, we say the particularly work when we view that by definition of work is that this interaction must be such that it is can be viewed as a rising or falling a body or certain mass. For example, if you have a source of electrical energy which is in the form of storage battery and we have a resistor. So, in this way we are consuming the electrical work, but this particular situation can be viewed that resistor can be replaced with a motor and that motor can be used to rise or fall a weight or body. So, that means this particular things we can view it as a work transfer. So, that is the reason all these electrical applications we can view in thermodynamically we call this as a work transfer. Now, let us see that when we are going to deal with the first law of thermodynamics, how energy of a system can change. So, when we are looking at the energy balance or first law of thermodynamics, when we are going to apply for energy balance system in an open or control volume system. So, as a by control volume I mean that there is a possible work transfer, there is a possible heat transfer. In addition to this, we will have also mass can come in and can go out. So, this is most generic definition or general definition that how energy can come into a control volume. But whereas when you deal with the closed systems, we do not have mass interactions. So, it is a very general way that normally when you deal with the energy balance equations, we take a control volume approach. So, if you look at this particular figure, so we have work interactions W, we have heat interaction Q, and side by side there is some mass which is coming up and some mass is going out. And in a practical situation there may be multiple entry of mass and multiple exit of mass. Similarly, there are multiple entries of work transfer and multiple entries of heat transfer as well. So, all sorts of things that can be summed up. So, very basic equation that can be derived from this first law of thermodynamics is that total energy entering the system minus the total energy leaving the system is not the change in the total energy of the system. Now, that means E in minus E out is equal to delta E. So, what is this E in and E out? E in minus E out can be from Q in and Q out, difference in the Q, difference in the W and difference in the energy due to the mass associated with the mass. So, when you sum it up these things, then we can get the left hand side equation of this equation in this form of heat, work and E mass in and E mass out. But what is the delta E of the system? System can change its internal energy U, it can change its kinetic energy, it can change its the potential energy. So, this is the very basic definition or energy balance equation based on the first law. Now, when we apply for it a closed systems, so we are restricting the mass interactions. So, there is no mass interactions and of course, when if it is a system is a stationary, so there is no change in the kinetic energy. So, it takes a very simple form between work, heat and internal energy, that is delta Q minus delta W is equal to delta U. So, in a small differential form we can say dou Q minus dou W is equal to du. So, here if you see, since heat and work are path function, so it is represented as inexact differential, whereas U is a property, that is internal energy. So, it is represented in the exact differential. So, these particular things, that mechanism of energy transfer I have already told, that energy interactions are recognized as when the energy crosses the boundary. So, it is a boundary phenomena. So, for a fixed mass system or core systems, it is in the form of heat and work. So, a system possesses energy, but it cannot, we cannot say system possesses heat or system possesses work, because these are boundary phenomena. So, heat and work associated with a process, not a state. Unlike properties, heat and work has no meaning at a states. So, it is wrong to say that heat at a state 1. And last one is that heat and work are path functions, because their magnitude depends on the path followed by a process as well as its end state. So, that is another concept called a perpetual motion machine, and in fact, this is hardly used word. So, the very basic philosophy is that if till date we have said that in fact all first law of thermodynamics is an experimental observations, and none of the system has violated this particular law till date. So, that means it is an experimental observations, and side by side till this point of time there are every system that agrees the first law of thermodynamics. Now, the concept or hypothetical term that is used, perpetual motion of machine, means it is a device that would produce work continuously with absorbing any energy from its surroundings. So, it cannot, we cannot keep on producing work continuously for lifetime, for infinite time. So, in such cases we say PMM1 is impossible. So, it is a very hypothetical term. Now, after understanding this, let me tell about the some elementary processes that we are used in the thermodynamic systems, and in fact, these elementary processes are very vital for subsequent applications in the steams, in refrigeration, in the gas cycle, in the IC engine cycles. So, all these processes are routinely used. So, what are the processes? So, basically there are constant volume processes, we call this as isochoric process. Constant pressure process, we say isobaric process, these are mostly used in the IC engines. Constant temperature process, which is isothermal process, it gives a indication that temperature, I mean the process is very slow, because a process has to take in a very slow manner to make the temperature constant. So, it is a isothermal processes. We also have a reversible adiabatic or isentropic process, and side by side we can also have a non-reversible process or simply adiabatic process. We have polytropic process. Polytropic process is something gives a very general definition which can take care all types of thermodynamic processes. And last one is a constant internal energy processes. So, here I will make an emphasis here that when we have constant internal energy, because till this point of time we say U is a function of temperature. So, means that whenever temperature remains constant, internal energy also remains constant. But in some situations, the internal energy in a non-reversible situation, internal energy may be constant, but temperature need not be. So, I will tell you some examples in the subsequent slide. So, let me say first one is constant volume processes. So, it is a isochoric processes. So, a typical example is that when you draw this isochoric processes, it is a vertical straight line in a PV diagram. So, process undergoes from 1 to 2. So, in this process your volume does not change. Typical example could be that we have a heat source, and this heat source, a system takes this heat, a system containing a gas of certain volume V is taking this heat. So, in this process what happens? There is no work transfer, that is dW is 0, but it is getting heat. So, dQ, that means entire heat is getting utilized in changing its internal energy or in the form of temperatures. So, when we are adding heat, so obviously temperature of the gas is going to rise. Another way of looking at the thing is that here when we have no heat interactions, like in this case there is a paddle wheel arrangements. So, we have a pulley, and by rising or falling this particular mass, we are regulating the what is going to happen within this container or this system. So, what happens here? There is no heat interactions, but the work which is being used through this mass is getting utilized in changing its internal energy. So, basically speaking, if you look at dQ minus dW is equal to du, then one situation your delta Q is 0, other situation is delta W is 0. So, if you have this delta Q is 0, then W can be represented as U2 minus U1. If delta W is 0, then Q can be represented as U2 minus U1. And of course, when you deal with the constant volume process, we must recall that there is a term which we are using called as specific heat at constant volume, that is amount of energy required to heat require as a heat to change the temperature of unit mass by 1 degree centigrade. So, that way we can define the Cv as a function of du by dt. The next process that we are going to discuss is about constant pressure. So, in a constant pressure process, it is in a PV diagram, it is a horizontal straight line. So, here there are two situations which is given in this example. One could be a reversible process. So, in the reversible processes, we can have a heat source, and this heat source is utilized to heat a gas or saturated liquid, and this particular system is in equilibrium with a mass m at certain positions. So, in first case, when we are talking about this du is equal to dq minus dw, so we can write it as this dw as pdv. Pdv means that when you are using this heat, the piston keeps on rising or falling depending on the amount of heat is getting added or rejected. So, side by side the volume of the gas or this particular liquid keeps on changing. So, we can represent that in the form of pdv. So, that is here it is written dq is equal to du plus pdv, and when u plus pv you can merge in a single term as a differential, and we give a name as a enthalpy, that is H is equal to u plus pv as dH. So, dq becomes dH. So, in a constant pressure process, heat addition is nothing but the difference in the total enthalpy. And we also can have another situation, define that specific enthalpy we can define in this manner. Okay. This is what we get in a heat addition process. Now, when there is no heat additions, so similar expression also can be drawn here, where the gas is controlled or the temperature of the gas is controlled through rising or falling mass system, and these particular things when you do this, basically instead of heat we are doing work transfer in the form of shaft work. So, here this work transfer is recognized as a difference in the enthalpy. Then moving further, we are now in the constant temperature and constant internal energy processes. So, in some situation what happens? Let us say when you have a constant temperature process, normally we call this as a isothermal processes. So, he means in an isothermal processes temperature do not change, so internal energy does not change. The energy transferred to the heat is exactly equal to work done by the systems. So, this is represented Q is equal to W, and W we can write it as a PdV. So, accordingly Q or W we can find out by integrating the system which undergoes change of state. So, RT ln P1 by P2. This is one aspect, but another aspect is that when you deal with the constant internal energy processes. So, for example, in that case you are saying that du is equal to 0, delta u is equal to 0, it is a constant energy process, and this can be achieved either q is equal to 0. So, if you take dq minus dw is equal to du, and if du can be 0, this will imply either dq is equal to 0 or dw is equal to 0 or dq is equal to dw. Both q and w are 0, which is very hypothetical, or dq is equal to dw. So, on such cases, but here it has nothing to do with temperature. If you see here, it is comes from first law, it has nothing to do with temperature. When dq is equal to d0, what is the situation? There are some situations the processes which are irreversible, for example, free expansion, mixing of two fuels at different states. So, these are the some of the irreversible processes where we are recognized as a constant internal energy processes, whereas isothermal processes is a reversible one. Then this is the example that talks about that how we can have a free expansion of gas. So, we have a gas in a container, and this particular gas is separated by two entities, one at certain pressure, press P and T, other is in the vacuum. Now, if you remove this partition, suddenly gas comes into contact. So, in this process there is no heat transfer, there is no work transfer, but and so internal energy is equal to 0. Another situation could be mixing of gas at two different temperature, gas A, gas B at different conditions. So, in that case finally U2 becomes U1. So, these are the some situations where we can recognize a constant internal energy or a constant isothermal processes. Another process, it can be adiabatic. So, adiabatic process is a irreversible one. So, the work done by the system is associated with the change in the internal energy. So, most of our systems are adiabatic when we say there is no heat interactions. So, that means the work done by the system is associated with the change in the internal energy. Now, moving to adiabatic, and there is another term, if you use the word reversible in its prefix. So, we call it as reversible adiabatic, then we say the process becomes isentropic processes, and these isentropic processes why we are recognizing, because it gives lot of important informations. Means that when we say it is an isentropic processes, so that means q is 0. So, du can be written as pdv. So, this du also can be talked about at Cv times of t. So, from this we can get the what is work transfer W. So, work transfer can be evaluated. So, in the form of pressure and specific volume. And of course, we also know another information that H is equal to U plus Pv, and from this we can get for an ideal gas a definite relations that the specific heat at constant pressure, specific heat and constant volume, we can frame a relations Cp, Cv and R, and they are recognized by this. Cp is equal to Cv plus R, gamma is equal to, that is specific heat ratio, that is Cp by Cv, and Cv is r by gamma minus 1, whereas Cp is equal to gamma r by gamma minus 1. Why I am saying this? Because this isentropic processes has many informations that we are going to use routinely in our all applications. Now, in a PV diagrams we can recognize this path of an adiabatic processes, and this can be represented the path, or we can describe the system as PV to the power gamma is equal to constant, and these derivations also come from the first law. So, the first law for an isentropic processes has very important implications. Now, after recognizing this particular thing PV to the power gamma is equal to constant, a more generic way of representing a system is a polytropic processes. So, instead of saying PV to the power gamma is equal to constant, we normally say PV to the power n is equal to constant. So, for a quasi-static processes which undergoes change in pressure and specific volume is represented as PV to the power n is equal to constant. Now, let us see what is its significance. Now, if you see, if you draw it in a PV diagram, so when n is equal to 0, so it represents a constant pressure process. If n is equal to infinity, it represents a constant volume processes. If n is equal to 1, it is equal to PV is equal to constant, which is an isothermal processes, and side by side n can be 2, and when n is equal to gamma, it becomes adiabatic processes. So, likewise we can have n has any number that can be specified for a given thermodynamic process, but however elementary processes has definite value of n. So, this is how we recognize these polytropic processes as one of the base to understand many elementary processes. The first law of thermodynamics gives another indications that what is this flow work. It is nothing but the energy required to push the fluid in and out of a control volume is known as flow work or flow energy. Normally when you say the first law or mechanism of energy transfer, mass entering and mass coming out from a control volume has certain kind of energy. Now, what is that amount of energy that you are going to require? That means how much that mass or which enters or leaves carry the energy. So, that particular term in thermodynamic sense we view or call as a flow work or flow energy. And this flow work or flow energy, and it is a combination of two properties, and in fact when some mass comes in, so we represent this as a term enthalpy U plus PV. So, that is the reason that when some mass enters into the system, and the flow work of course can be computed for imagining this particular mass as if it moves a distant cell. So, amount of force is required P times A, and this flow work can be nothing but PV, pressure into its volume, but thermodynamically we can represent this flow work by its enthalpy H, capital H, that is mass into small enthalpy, and this small h is nothing but U plus PV. So, if you see here, this enthalpy has two terms, internal energy, pressure and specific volume. So, it is a combination of property. So, the flow work is normally a combination property. And moving further, we have another equations which for a non-steady situation, when if you are going to deal with the energy balance, we make use of the principle that local equilibrium and average change in the property systems can be related to the energy transferred and work done. That means, rate of accumulation energy is equal to rate of inflow energy minus rate of outflow energy. So, basically we are using same equations of same first law, we are interpreting in a different manner, that is if the phenomena is a transient phenomena, it is dE by dt, change on the energy with respect to time. That energy that can come in either in the form of mass, that is me, and this is the total energy content, that is its enthalpy, its velocity and its potential energy, which is the exit, plus Q, and other kind of the energy that comes as the from mass from the inlet is Mi multiplied by its enthalpy, velocity and the gravity Z, and other kind of energy that we have is work transfers. So, this particular equation talks about rate of accumulation energy in the form of what we call as the energy of the system is represented as delta U plus kinetic energy plus potential energy. So, when you have this, then this particular energy can be expressed in the form of mass, enthalpy, velocity and height. Now, for a steady flow process, we can take out mass as a common, that means Q minus W by m. So, d by dt becomes 0. So, we can represent in this form, and finally, we can get a steady flow energy equations. So, this is a very fundamental equations in the thermodynamics and it has lot of implications. Now, this control volume can have a multiple exit and multiple inlet. So, that way we can put the exit as 1 to m and entry as 1 to n. For a single stream, that is one inlet one exit systems, we can say only mass, there is only one mass, that is mass flow rate remains unique or fixed. And finally, when the working fluid experiences in most of the situations also the negligible change in the kinetic energy and potential energy. So, we can say Q minus W is equal to delta S. So, what has been seen here that starting from the very basic equations, we have changed the nature of the equations for variety of applications. So, this is what the main significance or main inference that we derive from the first law. Now, why we are going to do this? Because we are going to discuss about steady flow devices that are commonly used. So, the steady flow energy equations can be simplified for variety of applications. So, first application is we are going to use in nozzles and diffusers, and usually the purpose of the nozzle is to increase the velocity at the cost of pressure, whereas the diffuser performs the opposite phenomena where velocity is decreased. And in same concept, we call this as a turbine and compressors. Normally nozzles are used to generate thrust, and instead of thrust, if you are looking at power, then same concept we can use it as a turbines and compressors. So, turbines gives the power output and compressor takes the power in as input. So, as a result its pressure is increased, but in a turbine the pressure drops. Another kind of steady flow devices, we can have a throttling valve. In fact, this throttling valve is used most of the refrigeration applications. So, there the throttling concept is that its enthalpy remains same. To keep enthalpy remains same, because enthalpy is a function of U and PV, that means U is also a function of temperatures. So, basically when enthalpy remains same, we can control the pressure temperature such a way that we can regulate the flow of a gas through a valve by keeping enthalpy is constant. And typical valve could be a porous plug, it could be a capillary tube. Capillary tube means a very small tube, or it can be an adjustable valve. Other type of steady flow devices are mixing chamber. Many a times you use a mixing chamber when two fluids comes, mixes, and finally a single fluid goes out. So, we call this as a mixing chamber. We also can have a pipe or duct flow. So, this particular say that there is a pipe or duct and in which a shaft is rotating so that it sucks the air. Normally this is used in a typical wind tunnel where there is a fan that sucks the air from one end and throws it away to the other end. We can view it as a pipe or duct flow. And most importantly, in the heat transfer, we are using very frequently use the word heat exchanger. So, in the heat exchanger, there are interaction of hot fluids to the surroundings. So, you can have a situation there is a hot fluid passing through a tube and it is interacting heat with respect to surroundings. Other situation could be there are two fluids, that is fluid A and fluid B. So, fluid A is entering in a pipe, whereas another entry fluid B is entering, but it is at higher temperature. So, as a result there is a heat transfer between these fluids. So, such a device we call this as a heat exchanger. Okay. So, with this I conclude the topic for the today. So, we have dealt with the first law of thermodynamics and its application for the steady flow processes. Other topic interest that we come out, that what are the different types of thermodynamic definition of work interactions. So, based on this particular two important inferences, we are going to discuss some few couple of problems, and the first problem is about a piston cylinder devices in which there is a gas of certain volume 0.08 meter cube and it is held in equilibrium through a linear spring. So, first let us draw the physical systems, what it should be. So, we have a piston cylinder device. What we have is this particular piston is held by a spring, okay, and that is a gas. What happens? This gas has volume V as 0.08 meter cube and this piston has cross sectional area 0.3 meter square and it is in equilibrium. So, what we do is heat is transferred to the gas. So, we are some means we are transferring heat into the systems. So, heat is added to the systems. So, obviously, this particular gas which is in this control volume or in this space, its temperature is going to rise. So, when it tries to push this piston up. So, when this piston is pushed up, the spring gets compressed by a distance x. So, the question that was asked, that what is the final pressure in the cylinder and what is the work done by the gas and fraction of work done against the spring. We have to use basically the first law and we have to find out final pressure, work done, and also we have to find out the spring work. So, what happens, how long we are, when we are adding heat, the final, so this is the final volume, that is V2. So, you can recognize that this is V1 and final volume V2 becomes twice V1 because heat is added, so that volume of the gas is doubled. So, final volume V2 is equal to 2 V1. Let us try to solve first problem, that is spring force. So, this spring force will give you the spring work. So, spring work is nothing but W half is equal to half K x square. So, K is also known here 150 kilonewton per meter. To solve this particular problem, let me start. What is V2? V2 is nothing but twice V1. So, it is 0.16 meter cube and we have area 0.3 meter square. So, we can find out what is this compression in the spring x. So, that is nothing but delta V by A. So, how much is change in the volume? That is 0.16 minus 0.08 divided by 0.3. So, the spring that is gets compressed, this will be about 0.26 meter. So, when you have this, then we can find out force, spring force, nothing but K times x. So, when you multiply 150 into 0.26, this number turns out to be 40 kilonewton. So, once we know this spring force, we can find out pressure induced, that is due to the spring, that is F spring force by area. So, area is 0.3. So, force is 40 kilonewton. So, this number would be 133 kPa, that is 40 by 0.3. So, 133 kPa. But initial pressure P 1 was 250 kPa. So, final pressure P 2 would be this spring this force, that is Ps plus P 1. So, this number would be 383 kPa. So, we know the final pressure. So, work done by the gas is nothing but spring work, that is W spring, nothing but half K x x square. So, x is known, that is 1 by 2 150, x is 0.26. So, this about 5 kilojoule. So, the fraction of work that is done against the spring is 5 kilojoule. The next question is about a nozzle. So, we have come across a steady flow devices which is a steam nozzle. So, if you can draw a steam nozzle with this control volume, it can be represented in this manner. So, nozzles normally accelerates the flow. So, its a contour is like a contracting section. So, the steam, let us say that enters the nozzle, that is condition 1. The steam leaves the nozzle at condition 2. So, when the steam enters the systems, its P 1 is 1.8 megapascal, temperature was 400 degrees centigrade, and it leaves at 1.4 megapascal and velocity is 280 meter per second. So, we have to calculate what is the inlet velocity of the stream, and in this process there is a heat loss Q, that is 2.5 kilojoule per kg. Okay. To solve the problem, first thing we have to use the fundamental equations mass flow rate. So, mass flow rate which is given to us is 5 kg per second, that is rho 1 A 1 B 1, and rho 1, that is nothing but A 1 B 1 by small b 1. Small b 1 is the specific volume. So, from the steam table data we can get small b 1 at this superheated condition as 0.16847 meter cube per kg. So, when you put and area A 1 is 0.02 meter square. So, this turns out to be, from these equations one can find out B 1 is equal to 5 into small b 1 0.16847 divided by area 0.02. So, the velocity would be 42.1 meter per second. Now, once you have this, then you have to recall the steady flow energy equations for nozzle. So, you can write this as m dot h 1 plus v 1 square by 2, because there is no potential energy here, is equal to q dot plus m dot into h 2 plus V2 square by 2. So, when you have all these numbers, okay. So, here from this first condition you can find out the enthalpy for condition 1, that value would be 3250.9 kilojoule per kg, that is from superheated table. Superheated steam table. So, in these equations we have all the numbers. M dot is known, that is 5 kg per second, H1 is known, V1 square is 42 meter per second, Q is 2.5 kilojoule per second, H2 is unknown and V2 is 280 meter per second. So, all the numbers are known except H2. So, after solving you can find out H2 value as 3440 kilojoule per kg. So, enthalpy is known. So, remember that we are looking at a steam that leaves the nozzle at P2 is equal to 1.4 megapascal and H2 as 3440 kilojoule per kg. For these conditions we have to use the interpolation. Of linear data from superheated table. So, this table you can find out any of the fundamental books I have referred, and here from this we can find out temperature T2 will be approximately equal to 380 degrees centigrade. Okay. So, that is the question that was asked, what is the exit temperature of the steam. Okay. So, with this I conclude this lecture for today. Thank you for your attention.